Hello. So here I am going to do one example with respect to discrete time Fourier transform. Okay, discrete time Fourier transform. From the example given by Dr. Udesh. Okay, so I think this first example is very similar to what we have done before. Okay, so here you are given one sequence. Okay, okay, so you can see that here you are given one sequence. Okay, so it is finite duration sequence. Okay, that means duration is finite. So here it is 0 to 4, 0 to 4, 1, 2, 3, 4. Okay, so la 1, no? So it is somewhat easy. So we have all terms as 1. Okay, so you have to find the Fourier transform of this signal. Okay, so you can use that identity. Okay, x omega is equal to e to the power e to the power sigma n minus infinity plus infinity. So here it is 0 to 4. N is 0 to 4, not minus infinity plus infinity. So n is 0 to 4 e to the power, sorry, xn, okay, e to the power minus j omega n. Okay, so this is the identity, and you know that this xn is always 1 for 0 to 4. So you have 1 here. Okay, and you have 1, okay, e to the power 0 plus 1 e to the power minus j omega plus 1 e to the power minus 2j omega plus 1 e to the power minus 3j omega plus 1 e to the power minus 4j omega. So you have these terms. Okay, so you can see that this is x omega. Okay, this is x omega. So this is the Fourier transform, discrete time Fourier transform of this sequence. Okay, this one. Okay, so very easily you can find this. Okay, and so it is expressed in another way. Okay, it is expressed in another way. So I think it's also not. So I think it is enough to. It is enough if you can write the sequence up to this level. Okay, I hope it is enough. You can get the full marks. Okay, but here we are asked to find the magnitude for plot and phase plot. Okay, so it is better to simplify this somewhat further. Okay, somewhat further, but as in previous case, I think this plot also very hard to plot. Okay, this magnitude plot and phase plot, or magnitude spectrum and phase spectrum, not easy to draw. Okay, because we have composite signal. Okay, so I think if you can find the expression, it is enough. So as we done in previous example, okay, in our tutorial, you can express this term using the Euler formula. Okay, using Euler formula, and you will have this kind of question. So here it is 1. Okay, 1, and you have this term, you have cos omega minus j sine omega. Okay, so here you have cos 2 omega, cos 2 omega, j sine omega, 2 omega, minus j sine 2 omega. Okay, and this part 3 omega, no? E to the power 3j omega, that means 3 omega. Theta is equal to 3 omega. So you have plus cos 3 omega minus j sine 3 omega. Okay, and here you have cos 4 omega j sine 4 omega. This kind of terms you will have, and you can see that this is the real parts. Okay, this is the real part, and these are the imaginary parts. These are the imaginary parts. So you will have as x omega, okay, number of cos term plus 1 some cos term as a real part. So this is real part. Say it is x, okay. Say it is r, okay. And here you have minus j, and you have some sine terms, sine omega, blah blah blah. Okay, so this is imaginary parts. Okay, so let's say I or something. So you have real part and imaginary part. So you can find the magnitude. Magnitude is equal to, you know that, r square, real part is square plus imaginary part is square root. Okay, so this is the magnitude plot. So you can see that it is very hard to plot here. And phase plot is capital X omega. Phase is tan inverse, okay, tan inverse real part by imaginary parts. So you have real part, you have imaginary part. So you can find both the expression easily. So if you find the expression, I hope you can get the full marks, because it is somewhat hard to draw. Okay, but here in this example, actually Dr. Udesh has used another approach. Okay, so it is so you can say that here the term is x1 minus e to the power j phi omega, 1 minus e to the power minus j omega. Okay, so this is you can write. Okay, so there is an identity. Okay, there is identity. I will use Windows Journal. Okay, so you can see that x omega, as x omega, we got 1 plus e to the power j omega, 2j omega, 3j omega, 4j omega, no? Okay, e to the power minus j omega plus e to the power 2j omega plus e to the power 3j omega plus e to the power minus 4j omega. So this is the term we get, no? Okay, so there is an identity like this. Okay, so x minus n can be write as, okay, x1, x1, x2 up to x n minus 1. So this is identity. I think this is called Taylor expansion or something. Taylor expansion or something. I am not sure. So anyway, we can check now. Okay, we will check it. So I'm not sure. That is why I'm going to take it. Taylor expansion, no? Taylor expansion. Okay. So there are many expansion. Okay. So anyway, please please go Google it and try to find. I am not sure this is one of Taylor expansion or not. Okay, so anyway, you can easily prove this. Okay, for example, if you have this kind of terms, okay, so let's say that yx minus 5 is equal to minus x, 1 by minus x, 1, x1, x2, x3, x4, like this. Okay, so if you expand it, okay, so you have to multiply all terms by 1. So you have 1, x1, x2, x3, x4, and you have to multiply all terms by minus x. Okay, so you have here minus x square minus x x to the power 3, x to the power 4 minus x to the power 5 or something. Okay, so you can see that x1, x2, x3, x4 cancel out, and you will have 1 minus x5. Okay, so this side equal, no? So you can write in this way, definitely. Okay, so you can see that, okay, here also, if you consider this e to the power j omega, as x, okay, that means e to the power 2j omega is equal to x square. Okay, e to the power 3j omega is equal to x to the power 3, and e to the power minus 4j omega is equal to x to the power 4. Okay, so here you have x1, x2, x3, x4. Okay, so you can write this as 1. So you can write this as 1 by x5 and minus x as this, no? Okay, so this way you can write this. Okay, okay, so you can see that this part is equal to 1 minus x5 by 1 minus x. Okay, so you can write this as 1 by x5 by 1 by x is equal to 1 x, x2, x3, x4, like this. Okay, so you have get that x as e to the power minus j omega. So if you again substitute here, you will have 1 minus x is e to the power j omega minus j omega, and it is in 5 power, so the power is multiplied here and divided by x 1 minus e to the power minus j omega, like this. Okay, so you will get this answer. So you can get this answer. Okay, okay, so you can also get this answer in this way. Okay, and also again we asked to find the magnitude plot and phase plot. So this term is again written like this. Okay, like this, and so here you can say that it is a to the power e minus j theta, like expression. So this is the magnitude. Okay, so magnitude of this total complex number is a, so magnitude is a, and the phase is theta, this theta. Okay, so here also they have found the magnitude, this is the magnitude, and this is the phase. Okay, this is the phase 4 meters. So you have find the form as phase. Okay. So they have found the magnitude and phase. Okay. So I think this type of simplification sometime not comes to your mind. Okay. So you can use this way. Okay. I think you can use this way. You can use some, but here it is some simplified version. We have simplified uh, magnitude spectrum and phase spectrum, but here also okay, okay, because we have found some answer. Okay, using a MATLAB also, it is sometime it is easy to plot, and here you can see this one is easy to plot. Okay, so the phase plot is easy. It is -4. Okay, so it is like this, no, till like this. Okay, it is y equal -x minus 4x type function. So it will look like this. Okay, if you plot omega with respect to this -4 omega, that is phi, the phase. Okay, so you will get this type of function. Okay, but here this one also it is uh, hard to plot. So you have to use MATLAB or something to plot this the magnitude spectrum. Okay, so I think you have both approach. I think this approach is somewhat easy because uh, all the things we know, all the things we use here, we already used in many times, no, previously. So you can use this method and this method, no problem. And I hope you can get the full mark. Okay. So anyway, I will try to do another question. Yeah, this is a place spot. It is somewhat like this is sine square type plot. No, this is sin is square, sin square type plot. Okay, and you can see that this is y equal to -4x type function. Okay. Mhm. Okay. So we will try to do this kind of question. Okay, and I think okay, I think this one is not much difficult. Okay, so here I will. So we have xn. Okay, I can. Okay. So this is our question. Okay, we will try to do this. So we will try to do this. So we asked to find the Fourier transform, discrete time Fourier transform of this sequence. Okay, this sequence, and you know that this UN is unit step function. Okay, so this UN is unit step function, and it is somewhat like this. Okay, somewhat like this up to infinity. 0, 1, 2, 3. Okay, so this is discrete time unit step function. Okay, so this is discrete time unit step function. Okay, it is look like this. Okay, and so if you multiply this 1.5 n by unit step function, you will get only these terms, no, from 0 to 1, 2, 3, 4, 5, so on up to infinity. Okay, so this n is like this from 0 to plus infinity. Okay, and you have this half by n. So if n is 0, it is 1. Okay, so n is 0, it is 1. No, So n is 1, that means it is half like this. It is half. N is 2, this 1 by 1 to the power 2 and 2 to the power 2, that means 1 by 4. So here it is 1 by 4. And here it is 1 by 8. And here it is 1 by 16. So on up to infinity. So at infinity, it will be 0. No? At infinity, it will be 0. Okay. So the sequence is somewhat like this. Okay. Like this. So it is start from 1. Okay. Like this, it became, and at infinity, it will become 0. Okay. Like this. Okay. At infinity. So this is n, and this is xn. So it is 1 here. Okay. And here it is half, and here it is 1 by 8, 1 by 16, 1 by 32, 1 by 44, 1 by 128, something like this. Okay. So this is the sequence. Okay. Discrete time sequence. So you have to find the Fourier transform. No? So it is very easy. You have to use that identity. Okay. So you have to use that identity. You have already that identity, capital X omega, Fourier transform of xn is equal to n minus infinity to plus infinity xn e to the power minus j omega n. So this is the identity you have to use. So you know that this is n from 0 to plus infinity. So 0 to plus infinity is there. Okay. So you have xn e to the power j omega n. Okay. So you have this xn is equal to again half n, okay, half n e to the power j omega n, okay, and it is from 0 to infinity, okay. So you can write some terms here like this, okay, half, half 0 e to the power 0 plus half 1 e to the power j omega plus half 2 n is equal to, that means half 2 e to the power minus j 2 omega, so on. You can write the terms up to infinity. Okay, up to infinity you can write the terms like this. So this is the Fourier transform of this sequence, and it is going up to plus infinity. No? Okay, so that way you can find the Fourier transform of that signal. So it is very easy, as you can see. Okay. So here you have given the answer. Okay. So uh, so you can see that. Okay. So this one. Okay. So you can see that we can simplify this further. Okay. It is simplified somewhat further. Okay. So you can see that x omega we have from 0 to infinity of n e to the power j omega n. Okay. So this can be written as, so this n and this n is common. So you can get this n like this. Okay. Okay. So you can so you can write the term this way. Okay. And So actually for this one also the that identity is used. I think you can understand it. Okay, so you can see that. Okay, so here you have, if we if we uh, expand this, so this type of uh, one you will have, okay, 0 e to the power j0 plus of 1 e to the power gn plus of 2 e to the power j 2jn plus of 4 e to the power, sorry, 3 here, 3jn, so on. Okay, so you can see that this is 1, okay, and this is half e to the power jn plus 1 by 4 e to the power 2jn minus 1 by 8 e to the power minus 3jn, so on. Okay, so you can see this. Okay, and if you find, okay, so anyway, I couldn't find any similar expansion here. So anyway, I think we can use the same knowledge. Okay. So anyway, you can see that. Okay. So you can see that. Let me delete this. Okay. Anyway, you can see that this is 0 to infinity half e to the power minus j omega n. Okay, so this is this type of function we have. So you can see that this is somewhat like this, e to the power j omega 0 plus half e to the power j omega 2, sorry, 1 plus half e to the power minus j omega 3, sorry, 2 plus half e to the power j omega 3, so on. Okay, so if you consider this half e to the power j omega as x, okay, as in our previous example, so you can see it is somewhat like this. So this is 1, no, 1, and this is x. Okay, so it is x, and here it is x is square. So we have x is square, and this is x, and x to the power 3, x to the power 3, x to the power 4, up to infinity. Okay, so you can see this kind of expansion we get. Okay, so I get this as like this. Okay, so you have 1 minus xn is equal to 1 minus x, 1 x plus x square up to x n minus 1. This kind of identity we have proved in our last tutorial. Okay, so you can see that this 1 by x2 up to x n minus 1 is equal to 1 by x n 1 by x, this way. Okay, so this identity you already know. Okay, so you can use the same identity here to prove this one. Okay, so you can see that this n is up to infinity, no? So this n is up to infinity. Okay, so you have this kind of so this n should be up to infinity, no? This n should be up to infinity. Okay, so infinity plus 1 actually. So again we have infinity, no? So we have xn, that means up to infinity. So you have x minus infinity 1 minus x, this kind of function. So if you get half e to the power minus j omega infinity, half e to the power minus j omega. Okay, so half e to the power minus j omega infinity means 0. This is 0. Okay, e to the power minus j omega infinity is 0. This e to the power minus j infinity is 0. So here you have 0. So you have 1 by half e to the power minus j omega. Okay, so this identity. That is correct, no? So we have this one. This omega we have get as capital omega. That is the only difference here. Okay, so you can get this identity, no, using that same expansion. Okay, so I think you can understand up to here. Okay, and in this question we are asked to use a new property. Okay, that property is time reversal property. Okay, uh, I think you can remember that in our tutorial, in our lectures, we learn only 3 properties: linearity property, time shifting property, and frequency shifting property. And this time shifting property is very easy actually. Okay, so so here you are asked to use the reversal property. Okay, time reversal property. So time reversal property is very easy. Okay, I think you better keep that property also in mind. So if you have xn time domain signal, if you get the Fourier transform, it is capital X omega and vice versa. Okay, so this is the Fourier transform pair. Okay, and this is Fourier transform pair. And time reversal property is stated that if you get x minus n, the Fourier transform pair will be capital X minus omega. So I think this is you can easily remember x minus n is equal to x minus omega. Okay. So this kind of property you have. Okay, so I think it is better to keep this property also in mind. So it property is also very useful. Okay, sometime this kind of question, this property may be given. Okay, because we didn't learn this property, but sometime you may given this property x minus n like this. Okay, so you may given this property, you may have given this property in your exam and you asked to use this property. Okay, so this is time reversal property. Okay, so here we are so this is our answer for this question. Okay, we have found the Fourier transform of this signal. So after that, we are asked to find the Fourier transform of this signal. So it is u minus a. So that means it is this side, no? This side like this. Okay. So this is un and this is n. So it is minus sign. This sign time reversal signal, no? Time reversal signal. So I think you have already learned these things with respect to continuous time signal. Okay. So I hope you can understand this. Okay. So it is just like an image, no? Image from this x-axis, image between this x-axis. Okay, time reversal. So this is the time reversal, and you have u minus n means this. Then you will have if you multiply this u minus n with half n, so you will have this kind of sequence. Okay, this kind of sequence. But later we have, I think you can remember, this kind of. So you can see that this is the image. This image with x-axis is this one. So this is the time reversal signal, no? So this is the time reversal signal. So you already know xn, you have found this, x omega, you have found it is equal to half e to the power minus j omega. Okay, half e to the power minus j omega. And you are asked to use the time reversal property. That means if you have any signal xn, the Fourier transform of that signal is x omega. If the Fourier transform of that signal is x omega, so time reversal signal Fourier transform will be time reversal of this Fourier spectrum. Okay. So this is the time reversal signal. Okay. So this is the time reversal signal. Simply a time reversal signal. No? So this x omega you already know. So you have to find x minus omega. That is time reversal of this signal. Okay. So it is 1 by half e to the power minus j omega. Here it is minus omega. So if you put the minus sign here, minus omega, that means minus minus, you will get plus. So you have plus j omega. So this is the time reversal Fourier transform. It is j omega plus j omega. Okay. So that is the Fourier transform of this time reversal signal. So I hope you can understand this thing easily. It is not much difficult. Okay. So I hope you can solve this kind of question. Okay. Using time reversal property also. Okay. So if you have any problem, if you can't understand what I am talking, you can simply ask or mail me. Okay. Then I can explain it again. Okay. Okay, we will try to solve one more question.